We are not the last one. Take the microphone.
This one?
Yeah. It's already switched on. No?
Oh, not that.
Well, at least it's not a solution.
It's okay, only the first question has been written.
Well, we welcome Eugene to our complex system seminar. After last week, Braden was giving us the highlights of his complete PhD. Eugene is going to talk about one of the many aspects of his PhD because, well, unlike Braden, he doesn't have a theme. So
40% of the PhD.
But especially the 2 students or 3 students who are in 486, feel free to ask nasty questions. Yeah? 2 students?
You're taking attendance now, right?
1, 2, 2? You don't count. Shall I start?
Yep.
All right, thanks for coming. My name's Eugene. I'm one of... Huh? Oh, no, don't worry. I'll promise to try and get through by the 45-minute mark, so you'll be able to capture everything. But I'm one of Michael and Thomas and Deborah's students. And today, as Thomas alluded, I'm going to talk about one aspect of my PhD because I couldn't decide what to talk about. So I'll be talking about the topic of embedding reconstruction and specifically studying data, time series that contains multiple scales. So I would like to begin first with a bit on embedding theory. So what is an embedding and also what's the embedding problem? The context we're going to set ourselves here is suppose we have some kind of physical system. I have an interesting diagram on the bottom left. And in that system, we can take time series observations. And we want to construct a model for this to do something like state estimation or prediction. The problem is the physical system could be a really high dimensional system. When we observe things, we inherently decrease the dimension somewhat, which means we lose kind of some information. And we want to then predict the future state of that via some kind of modeling process. But the main issue we need to contend with is in observation, we basically reduce the dimension a lot. How do we deal with the fact that we have this dimension reduction and how do we compensate for that? So we can kind of reframe this in terms of a few ways. So the first way is how we can ask the question of how can we reconstruct a full state evolution? So the state is the thing that we can't, is a physical aspect that we can't directly measure accurately, but the full state of evolution using only partial observations of the state. So here we're using observations as x. And we can also say in terms of prediction, given some observed history, how can we predict the future state sometime in the future? The problem is The problem is for incomplete observations, in the case you can't see the full state of the system, your dimensionality is reduced, that's the first problem. We also don't know necessarily how big the dimensions are. In the first case, you can kind of see maybe it's 3D. But in real world systems, we don't know what the dimension is. And we also want to be able to fully utilize all the information that's present within the data. So how do we tackle that? Come this very nice tool called embedding, and I have a nice-ish definition up there, but it's probably easier to see from the diagram is if suppose we had some kind of physical state space here, in this case it's 3-dimensional, you might recognize it as a Lorentz. Now here the state evolves according to some kind of differential equation, that's fine. We observe it, which causes, basically we observe a time series, which means maybe we observe the x component. Now we're going to do something, which I'll call psi here, but that's something, suppose we can convert this time series, which is 1-dimensional, back into something that's 3-dimensional. If the dynamics on this 3-dimensional reconstruction is diffeomorphic to the original dynamics generically, then we basically say that whatever that operation I did down there is a valid way to embed the time series. And here I wrote TDE mostly because we'll be talking about a specific form of it called time delay embedding. But the main takeaway from this is the fact that even though I can't observe this full state, if I can construct an embedding, that means I can just do all my work in the right side, the top right, and all the conclusions from the top right will be true in a real system in the top left, which means I can now make use of this time series in a meaningful way. Now, this is typically done in two different ways. The first way was actually where the original method of doing this embedding came from, which was essentially, if I have some time series, I'm going to augment the data to be multidimensional by having lag components given as such. It's nice, it's simple to understand, and it's simple to implement, and you only need two parameters. How many dimensions and what's the size of the lag. Generally performs well, but it's inflexible when you have to deal with data from multiple timescales, and I'll go through that in a moment. But an alternative for this, in a more general case, would be, suppose we just take different lags. So the lags don't have to be uniform this time, they're not multiples of each other. I can take tau 1 to be, yeah?
Just wonder, how do you define if they are isomorphic? What's the definition of isomorphic?
Diffeomorphic. Oh, so basically, I can define an invertible transformation between f and f, big F and small f.
Unique.
Yeah, yes, unique. So back to the non-uniform time delay embedding, I could have the first lag being 5, the next lag being 7, the third lag being 105. In that case, it's non-uniform, and it is a more general case of the uniform. Now, the nice part about this is that for the first case, the uniform case, in 1980s, basically, this guy called Takens proved that if you did a lag, uniform lag, you would basically confirm, you would guarantee that the embedding will be an actual valid embedding and all your dynamical features will be preserved, generically speaking. Now, the non-uniform time embedding case, it is done, but there is no proof to actually show that it is definitely going to work, but we just do it in practice. It's kind of relatively recent in the last 20 years or so, but predominantly people still use uniform time delay embedding because it's easy to implement. You only need to define two parameters. Now, the big challenge for this is parameter selection, because it's all nice and well and good if you take a tau, take an m, and actually in the original formulation of Takens' embedding theorem, it doesn't matter what tau you pick. You can pick whatever tau, and as long as your m is large enough, it's fine. Reality is not so simple, mostly because oftentimes the data is finite and the data is noisy. To see how this affects it, suppose we have some kind of sine wave as such. I've colored the lines to be according to the phase. And the idea is, if you did a very small lag, basically the components are going to be highly correlated, and essentially you get a signal or a reconstructed phase space that lies along the diagonal. Now, if you had noisy observations on that diagonal, you basically have an very ambiguous approximation of what the phase is. It could be, if you see here, it could be on the yellow phase, so it could be a phase of 2 radians, or it could be a phase of 6/0 radians, depending on how bad your observation noise is. So if you choose your tau badly, you could be less robust to noise in practice. If you choose your tau well, you basically get a really good approximation of what the phase is, which is essentially the main coordinate of this time, the main dynamics of this time series. So these are the considerations we need to have when we think about considering embedding parameters. So embedding should be well unfolded. We also additionally want our timescales ideally to be interpretable. So we want to see what the relevance is to the dynamics in the time series, and hopefully we can extend it to higher dimensions as well, because not everything is good enough in 2D. So I'll go through a brief, very, very brief overview of the history of embedding theory, just to give like a storyline of how it happens. Now, so 1980s, Takens came up with that theorem that proved that uniform delay embedding is good. And we had a whole host of things after that for developing the theory and developing methods on how to select tau and m. In 1998, we actually have a paper that now starts looking at non-uniform delay embedding. with ideas from minimum description, model description length. Then there was more time from 1991 to 2011, which was mostly dedicated to uniform delay embedding. So if you see a lot of ideas such as fill factor and the like coming up around that time. But then what we see is in 2007, there is, and I think around 2005, there are papers that start looking at non-uniform delay embedding methods. And around that time, we see just slow but steady growth of different methods of how to tackle this. So that's just a context for that. But just before I leave uniform embedding theory in the dust, the traditional approach, if you ever want to apply it, is just like your tau, you can do a few different ways. You could take if there's a dominant period in your time series, you could just take a quarter of the dominant period. So depending on time series, you could take a Fourier transform, take a quarter of the period there. You get the L statistic, which measures your sensitivity to the noise for prediction. Or what's very common, you could just take the auto mutual information. Take the first minima, and that's the tau that you pick. And for embedding dimension, you would just take a global false nearest neighbors approach. And if you do all of that, you might be able to get something on the right. This is an example of a 4-dimensional attractor, reconstructed from just the first components from the first dimension. It's not quite in phase space. It's in approximated with a network, but it looks prettier than the original phase space one, so I decided to use that. But if we go to non-uniform embedding, now we have a lot of problems, and this is actually why the development has been a bit slower. Firstly, is because even though it's more versatile for multi-scale dynamics, it's actually quite difficult to optimize because now you have to select a combination of lags tau 1 to tau m-1. And the embedding is not guaranteed by Takens. And another issue is that if you select different lags, how would you interpret them? So if you're doing periodic, yes, you can do a Fourier spectrum and see which lags are relevant. The challenge is when you have things like chaotic, non-stationary, all these kind of issues, it's not quite clear how you select those lags and how you relate them to the time series itself. And when I say multi-scale, I mean things like this. So for example, in ECG, it is a bit more regular, but you can see there is, for example, one loop here that's a bit smaller in amplitude and a big periodicity that's larger in amplitude. It's more obvious in the lobster data, where you clearly see there's one very slow but very large amplitude dynamic, which is that repolarization occurring for the neuron. And these small amplitude but high frequency oscillations, which are significant, but they correspond to the bursting fire of the neuron itself. So one way to look at this would be using a geometric approach. And so this was part of my research where we developed a method called stops. And it starts way back from a very simple idea of the quarter period heuristic. So if you had a periodic signal, for example, a sine wave, one common heuristic that you would go with is whatever the dominant period is, take your lag to be a quarter of that. And this comes from the fact that for a sine wave, you get a perfectly nice circle if you took a quarter period embedding of that in 2D. And it actually corresponds to the minimum of the mutual information as well. So the stops method, which we call significant times of persistent strands, you can think about it a little bit like a more complicated Fourier transform that's done more from a geometric perspective. So essentially, we're going to try to find all the quote-unquote periodicities or pseudo-periodicities of the signal and use that to inform the selection of the lags that you're going to choose. Essentially, the test we're doing is we're going to ask is, does a given lag correspond to periodic or pseudo-periodic behavior in the time series? And the algorithm goes as such. So first, we select the tau that we're interested in testing. Then we sample a contiguous portion of the time series of length 4 tau. Remember, if the tau lag we're thinking of is tau, that would be a quarter of the period that we're testing. So we multiply it by 4. And what we're going to do is just going to do a 2D delay embedding just of that strand. And we're going to ask, does that strand form what we call a significant circular object in phase space? Now, there are a lot of issues with the word significant circular object because how do you detect a circular object and how do you tell if it's significant? But if we can answer that, if yes, then we say tau is a characteristic timescale of x of t, and we give it a score as appropriate. Otherwise, we say it's not. We repeat this for sample of different strands from T. Repeat this until we can come up with some kind of profile across tau that tells you how significant each time scale is. Now, to answer the question of is there a significant circular object, the first kind of natural way would be, well, why don't we just detect when points recur within some neighborhood of each other? That is nice, except it double counts trajectories, so that's an issue. The other approach basically comes from the fact that there's been a growing interest in topological data analysis. And one way in that field is that there's tools to actually detect what we call holes in a given data set, in a given space or a given manifold. So we can think about it as trying to find the maximum persistence of the H1 homology of the embedded strand. And I'll go through that in the next slide because I know homology may not make sense to a lot of people right now. So what I mean by homology is, suppose we had 7 data points. So maybe these are the 7 data points corresponding to strand that you've sampled. What we're going to do then is we're going to select an, yep. Huh? 8. 1, 2, 3, 4. Sorry, 8. There should be then 8 blue dots. Sorry, 8. Yeah. So for example, this we're testing a tau of 2, for example. In this case, we grow basically these little epsilon balls around every single point. And we're going to track 2 quantities. The first quantity is how many disjoint objects are there. Because when any given 2 balls touch, we're going to join those 2 objects together. So here we have 8 disjoint objects. And then at some kind of size of epsilon ball, these 2 objects join. So now we only have 7 there. And eventually, we will all combine to have one object that is on its own. But more, so that's, we call the H0 homology. So in the 0th order, that corresponds to the number of disjoint objects. The H1 homology is actually the number of holes in the simplex that's formed. So for example, here there are no holes. There are still no holes here. But at some critical epsilon, there is a loop that forms between these objects. It's still one object, but there is a loop that forms here. So here, we say that there is one object, and there's also one hole, one void present. Sorry, one hole, not one void, present in this data set. And that's basically what what aspect of persistent homology we're going to use. We're going to track how these features get born and die for the different values of epsilon. So thanks for Michael, for pointing out that I am missing one blue dot here. But essentially, we're interested about the holes. The holes that hole that forms here can be thought of as a diagram here, where the horizontal position is the epsilon where that hole first forms, and the vertical position is where that hole disappears. If you want to ask how long did that hole exist for, we basically look at the diagonal length there, which is what we call the persistence or the lifespan, the lifetime of this homological feature. So back to the question, is there a circular object? Well, we can construct what we call a persistence diagram, which is this thing down here. And for each object on the persistence diagram, we can calculate its lifetimes. And so the maximum persistence H1 homology is, remember that strand, I'm going to calculate the persistence homology of that and find the lifetime of the most longest living, object, hole. And if it meets some kind of threshold, I'm going to take the value. If it doesn't meet some kind of threshold, it's not significant. So that's detecting whether there is a circular object. The next part is to classify or assess how significant is this circular object. So basically, when we were doing this naive approach, we found that, well, there are basically 4 main cases that you have. The first case is you have a hole, but it's kind of like an artifact of a really long spaghetti hairball. And so the hole you get, first of all, it's kind of not really that circular. And also, it doesn't efficiently use up the whole strand of the time series, which means the length of the strand is actually doesn't correspond to the actual periodicity you see. Now, the other case then would be, well, you use the strand really well, but it's not maximally unfolded. So it has high efficiency in terms of using the data, but it is not very circular. So this is a significant hole, but it's not the best you could have, so you give it a slightly lower score. The other case would be you have a nice circular hole, but then you have a long tail that comes after that. That's actually characteristic in the lobster data. Imagine early on, right before it spikes, there is a long repolarization tail, right? So in this case, you have high circularity, but it doesn't use the length of the data very well, which means the time lag or time scale you're looking at is not closely tied with the data. The best case, obviously, if you find a nice round hole or nice convex shape that efficiently uses the length of the data. If you call circularity alpha and efficiency beta, essentially you take the product of these two and you can use it to calculate a score, which now you can use to rank how significant is each time scale. So I understand that's a bit of a pun because it says stops in action. It was not intended. It was in post. I was like, that's a fun joke. So what we're going to do is we're going to test stops on 3 different types of cases. The first one is a sum of sine waves, where it's essentially a periodic-ish, well, it is a periodic system, but the amplitude of each component sine wave is different. So we have multiple time scales and amplitude scales. Then we go to a chaotic case, so Lorentz. And the last case we're going to look in this for stops is a lobster neuron, where multiple time scales, in addition to that, the magnitude of these dynamics are disparate. So you have a really big amplitude, slow dynamics, and then small amplitude, fast, high frequency dynamics. And we're going to compare a few of the embedding methods, the traditional mutual information profile commonly used in uniform time delay embedding, and then 2 other comparison methods, which are a bit more recent, which are methods for automatically determining non-uniform lags. And I won't go into that too much detail here, although I'll be talking about continuity statistic later. And how we're going to assess whether these embeddings that we make from different lags are better or not is we're just going to see how well we can do free run predictions with it. And when we say free run predictions, we are literally just fitting feed forward neural network to predict it. The simplest model you can, and we want to see whether these different embeddings actually encourage or affect the learning or the prediction ability. Now, there is a lot of stuff in this slide, but I would like for you to just focus on, well, the time series looks like that, but just focus on this third window here. So in this third window here, you have the component circularities, which is in blue, and efficiency in red. Horizontally, you just have different lags that you're picking. And you have these small peaks that essentially correspond to the first one of the 2 frequencies, and another peak at a little later lag, which corresponds to the longer time scale as well. And what's interesting is if you look at the mutual information, you will not actually get a lot of information. You will not get any useful bits out of it. So that's what the mutual information profile actually looks like. So seems to work all right. What happens in chaotic? In chaotic, we see a much stronger case, but we know this is a case where mutual information does do well. The minimum of the mutual information corresponds quite well to the first peak. That's what we want. Nothing special there. And the periodicity, the tau you see here actually corresponds to one of these oscillations occurring there, right? The interesting one happens when we start looking at the multiscale dynamics. So here, we should expect some time scale on the very, very small end, and one time scale on the very, very large end. Here we see mutual information fail spectacularly because there is nothing to tell us that there is a minimum there. But for the significance score, we see this peak that occurs, which actually corresponds to that very small scale dynamics at the start, followed by a peak later, which is at that repolarization dynamics. And it's interesting to note that compared to the uniform delay, the non-uniform methods, essentially it starts fooling around and it can't figure out what time scales. It does pick out these ones here, but it fails to, it struggles to pick this small one here. Although I must mention that the Pekuzal method here, which actually uses, partly uses a method called continuity statistics, there is work that's been done that you can do it such that it can detect with a bit of tweaking this peak here, but it struggles. You need a bit of tweaking for that, but it is possible. If you're curious to see what the embeddings look like in 3D space, we took the two comparison methods, which is Pecuzal and MDOP, and we compared it against our stops method, where we selected just the two timescales. Now they look pretty similar, but you don't actually see the multiscale dynamics as clearly. If you were to take the two timescales separately, you'd get, for example, one loop here, which basically you take a vertical top-down view of that. You get one loop here, which is clearly that small timescale dynamics, the small timescale pseudo-periodicity. And then you get the big loop here corresponding to the slow dynamics. Now the reason we looked at this was because we said, well, does this actually help us learn things better? Turns out, yeah, maybe, can't tell. But if you looked at the prediction, for Pecuzal and MDOP, these periodicities don't actually get shown in the prediction. So these are 10-step free-run predictions, but the oscillatory behavior gets captured ever so slightly better in stops. Still not very convincing. But the idea here is it's more flexible than a Fourier transform, and it's interpretable because now you can relate it to periodicities. The problem is it's computationally really expensive, and doesn't really tell you how to select multiple legs. It just tells you which legs are important. So can we do better? And I'm going to take this time to just go back to what I said Pecuzal. So Pecuzal, specifically one component of Pecuzal, the Pecuzal algorithm, which is the continuity statistic method. And this basically comes from a family of embedding methods called the unified optimal embedding approaches. Essentially, they wanted to come up with an algorithm that you feed in a time series, it just spits out in order the significance of different time legs that you should use to construct the embedding, and automatically stops when it thinks it should stop. And how it goes is you start with some selection of legs. So initially you start with no legs. You evaluate some statistic, use that statistic to find a lag, add it to the system, repeat until you have some ending criterion, and then you terminate. The innovation that happens is basically how you find your optima and what statistic you use. Because depending on what statistic you use, that's your definition of what's considered an optimal embedding. Now, there are a few methods that basically came up here. Sorry, that should be 2005. A lot of different methods. I think the most recent one is the one by Kramer in 2022, which is not publicly implemented yet. But I would like to focus on one that was actually proposed way back in 2007, which was also successful in analyzing the lobster time series, which was the continuity statistic. Essentially, it says, if I'm going to add a specific lag to my embedding, I'm adding a component to my delay vector, that lag should be as functionally independent as possible to the components that I already have, because I don't want redundant information. I want to have as little redundant information as possible, so I'm really efficient with my embedding. So essentially, we're testing for some kind of general nonlinearity F here. And that's basically what we call the continuity selection criterion. If there is an F, then that's probably not a good selection. If we can't find an F, then maybe consider adding that new lag in your component. Now, clearly, it's very difficult to find this F because it's so general. What Pecora, who proposed the continuity statistic, said, well, let's utilize the fact that we assume that F is a continuous nonlinear function, which means it's smooth. And so, if I have some kind of neighbors within some neighborhood in an existing embedding that I have, if I look at the component I'm about to add, I want to see how many of them lie within some epsilon of that same reference point. If there is a lot of crossover, it implies that whatever this F is, which must be complicated, is at least smooth, because epsilon ball maps to epsilon ball, or intersection of epsilon balls. And they test this with respect to some column of null hypothesis, which is just binomial. So other simultaneous membership of these two sets, are these blue points in here by chance or by the fact that there's a functional dependence there? And this is just a little table I stole from there. But essentially, if you have 5 points in here, to reject the null hypothesis that's by chance, you need all 5 points to be in this ball here as well. And the numbers differ as you increase the number of points, because it is with respect to some kind of confidence interval. And essentially what you're going to do is calculate various epsilon. So you get a profile for the average epsilon you need to guarantee this kind of continuity for different values of tau. You'll get a profile, and that profile then is then used to estimate given lags, and you do that iterative scheme. The problem is this approach requires you to define some kind of confidence interval, which is fine, but we're trying to maybe, can we improve on that essentially? And this kind of leads to a more general problem, because if I'm trying to test for functional dependence or functional independence, I want to see whether there is a nonlinear correlation between the components I've already selected and the component that I'm thinking about adding to my vector. So let's go to a more simple case. Let's talk about linear correlations first. So I'm not a statistician, so I might have got some notation here incorrect. But if we wanted to find the correlation between two time series, we could have it in that form. That gives you a linear correlation. And if this functional dependence is linear, we would expect this to be plus or minus 1, this expression here. Now the trick is, we wanted to detect nonlinear, right? Because linear is easy. We want to detect nonlinear. And this kind of general problem of nonlinear correlations or cross correlations is looked at in this area of statistics called canonical correlation analysis. And initially they were looking at linear correlations, which was asking what is the best possible combinations of two time series x and y, linear combinations of them, such that the components actually have maximized the correlation. Now this is a linear case. And the trick here would be to find the best weight vectors u and v that combine components of x and components of y, different random variables, to maximize the correlation. But we don't want linear. We need nonlinear. So I'm going to skip a whole bunch of in-between literature, but look at something a bit more recent, which was from machine learning, which is, well, what happens if we just increase the library of functions we're looking at, and we try to find the best nonlinear function of the input x, the best nonlinear function of input y, and also the best weight vectors that can be used to maximize a linear correlation. What we're doing here is we're dealing with the nonlinearity beforehand, such that these two combined form two separate variables, or auxiliary variables x and y, which hopefully are linear correlated using a kernel function. And then they decided to actually improve on that, where we have now deep neural network version of that, where we just replace the kernel function with a really deep neural network. We replace the correlation with this loss function, which is basically just a correlation, and we can just do a whole bunch of training on that because we have the computational resources to do it. That's all well and good, but it's very computationally expensive, so let's simplify it a little bit. We want to do it for nonuniform embedding because nonuniform embedding requires quantifying non-linear functional relationships, and we need it to be robust to noise because realistically data is noisy, and want to be computationally scalable. So let's simplify that deep neural network stuff here, right, into something a little bit simpler. We can just define, we want to find the best possible nonlinear function that becomes of one variable that becomes linearly correlated with the other. So this equation essentially has f. F is just a nonlinear function that's learned by some kind of neural network, and we're going to train a neural network to best predict y from x, calculate the correlation, the linear correlation, and that would be what we call a general nonlinear correlation. It's basically a simplified version, a simplified asymmetric version of this DNN, deep neural network CCA. And it works pretty well. So on the left side, we have two things that should be nonlinearly correlated. So something is a polynomial function of the other other parameters, so x and y. Clearly, linear correlation would fail very quickly, but nonlinear correlation should be perfect. So in this case, it's just a function fitting problem for the neural network. So we expect it to work well. What we expect to work a bit differently is if you had basically maybe contiguous portions of the time series which are not we're not one-to-one or not many-to-one. So here if you go from left to right, I'm just taking different lengths of this, different proportions or lengths of this circle. So it starts with only this small bit, and then by the end, I'm considering a trajectory that's a whole circle. And at a halfway point, we expect this nonlinear correlation approach to start failing because we start entering the territory of having data that is now many-to-many, functional relationship that's many-to-many. And indeed, it has a correlation that's 1 all the way until that point. So maybe it's doing well. So how could we then utilize this to evaluate to figure out what lags to choose in embedding? Because in the continuity statistic approach, we want to find lags that are as non-linearly uncorrelated as possible. First of all, we've got to deal with the fact that it's not that this GNC approach is asymmetric. So we test both directions, right? We test the correlation between a component and its lag version, and then the other way around. We take the best correlation between the two. Now we have a profile as a function of the lag that we want to assess on how correlated these two components are, and we can take the first minima as embedding lag, repeat that, and you get an iterative approach. This is just an example of what those profiles would look like. In green, you have your standard mutual information. In red, you have your linear correlation, which fails really badly for Lorentz. And in blue, we have basically this simplified GNC neural network idea of nonlinear correlation. We see that's a similar pattern in both, in mutual information and GNC. So you think, oh yeah, first round seems to work. What happens when we use this to select tau? It does not do very well, to say the least. Suppose you take that first minima. Cool. You now try to calculate the next profile, condition on that first tau you've selected. And what you see is, well, firstly, there's not much change after that. And actually, the fact that that the correlation stays almost close to 1, there's a good reason for that, which we'll see later. But the main issue we have is not only is this method very computationally expensive because you're fitting, in this case, 100 lags or 100 neural networks, you see a lot of volatility happening because of the poor initialization of the neural network, which occurs by chance. So can we simplify it further to make this actually a usable method? And here is where we discuss maybe a different method called, maybe something from entropy. Because why not? Entropy sounds cool. So as mentioned before, GNC is very computationally expensive. Poor initialization means you get volatile results, which is not good. And it performs particularly badly when the attractor is unfolded, which is in that region where your tau is really big. So we're going to relax our requirements of whatever measure we're going to take even further. We're going to say, let's say it's a nonlinear function, so at worst we're only going to consider a many-to-one relationship. Okay, that's the first case. And we don't care about the functional form at all. We just want a score that tells you whether or not a many-to-one relationship is prominent somewhere in your embedding. I would go through this step by step, but in the interest of time, I'd rather go through the picture. So what we're going to do is, suppose we already had an initial embedding. Let's say X is our first embedding, and we want to consider a potential tau. So this is the very start of how you initialize it. Now, we're going to look at this point here, which is our reference point. And we're going to find it's 1, 2, 3, 4, 5-ish, 5 nearest neighbors in this X component. Its 5 nearest neighbors are going to be here. Remember, we're going to ask, is there a many-to-one, is there a one-to-many relationship occurring here? Because if there's a one-to-many relationship, it means there is some kind of funny things going on, and we probably want to consider that time lag occurring in our embedding. What we're going to do is, now the continuity statistic would have found the biggest epsilon to cover these two balls, and then that will be a statistic. But as we said, that requires you to test membership with respect to some null hypothesis, which is a bit cumbersome. So what we can do instead, we're going to basically look at all these points. This is the component in xt minus tau, and what we're going to do is we're going to place little Gaussians on top, sum out the Gaussians, and basically we get a distribution here, which we're going to find the entropy of, the p log p of this distribution here. And essentially what that allows us to do, it comes up with a measure that tells us whether or not you have bimodality or uniform or single modality, which is a measure of how one-to-many a given section of your embedding is. Do that for every single point, and you get a measure like that. And now you can take some kind of average across this embedding to give a score for how good or how bad this tau is. Where a lower score means there's a lot of one-to-many relationships happening here, which means you might want to consider that tau as a potential candidate. If it's a high score, you don't need to. Sorry. High entropy means you want to consider it. Low entropy means you don't. I got it the other way around. And so that's the approach you're going to do it. And this is actually what the results actually look like. So in the first case, you calculate that profile, which is that entropy profile with respect to tau. And you actually find three maxima here. Now you want to test which of these maxima, if you were to include it in your embedding, results in a new profile, i.e. this red one here, that has the lowest possible minima as you can, because you want to minimize this entropy measure as much as possible. Low entropy means functional dependence. So with this result takes the first leg, and what we get is a nice embedding like this. Now you might ask, well, where's the second? Shouldn't there be at least two legs of the three-dimensional system? There should, but recall, if I'm going to go back, recall way back, we were asking, well, is this actually significant, right? The first leg is pretty important, but the second leg basically stays very close to 1. So basically what we see is that the fact that it doesn't pick it up is because adding an additional leg, it does help, but most of the gains are actually from the first leg component. You might get a small gain in adding a third component, but it's not very big. And so for this method, it actually doesn't pick up that benefit. If you were to take this leg and you plot it, that's the embedding you see. Pretty nice, pretty unfolded. Bit of a harder case, we have a Chua double scroll system. Now, this plot, it's the same plot except we actually go through 3 embedding cycles. So in the blue case first, it sees 2 maxima. It evaluates that this one produces the next best entropy profile. Then it goes, which produces this orange brownish one. And it finds that maxima there, which produces the green one, which finds that maxima there, and it produces the final profile we have in red. And these actually do correspond quite nicely to the dominant periodicities in the signal as well. And we get a nice-ish unfolding of the attractor. This one's a more interesting problem because the Halvorsen system is also a 3D chaotic system, but it's also an example where mutual information, if you try to do a uniform embedding, fails spectacularly because the mutual information approach doesn't guarantee a minima, and for this case, there is no minima. Or rather, a minima doesn't present itself very clearly. Interestingly enough, this entropy approach actually gets a nice maxima that occurs here, followed by the same idea, go through. And if you do the embedding, you actually get quite a nice unfolding of this attractor. Now, briefly, you might ask, why is it do we take the minimum, as in when we evaluate a profile, why do we see how low it gets? It's because if you take the average, it means you're going to be taking average across tau values. There are issues with that because now you have to select the correct region of tau. By taking the minimum, we don't have to make that selection. It works really well with ECG data as well. So the ECG data you saw, it gets one kind of dominant periodicity, which is that whole single loop, and the small repolarizations occur as well. It gets that. But the lobster data is the fun one. So we get that big periodicity here, which is your repolarization, depolarization. And we also, this method seems to also find that small time scale information there as well. And apparently a 91 somewhere there. And so now we have this method, which built on a mixture of ideas of continuity and the stops method, which is a unified approach, finds you some lags, and now has one parameter less for you to decide, which is your significance level. Summary and conclusions is that embedding reconstructions are useful. If you want to model stuff and in an efficient way, you could chuck a neural network, a really, really big one, and train it for a really long time. You'll probably do well. But if you want to be efficient, that's one way of doing it. Non-uniform delay embeddings are more versatile, and if you can make it interpretable to geometry, that's even better. And we've basically finished off with combining all of that into a new statistic, which is entropy, based on entropy, which is simple-ish to implement and seems to work. I think that's 46 minutes, so I'm 1 minute over time. Yeah.
Thank you, Eugene. I'm pretty sure there are some questions out there for you. Any questions from the audience?
We'll start by answering the nitty questions.
Yeah.
We're looking at a data series from all bodies, mineral systems, and we think the dimensions might be 7 or something like that. How do you think this would operate with that high dimension?
So, so this case here, it should work well in high dimension as long as you can find your near neighbors, which shouldn't be an issue. The only problem that I would foresee occurring is that when you do a high dimensional embedding, you actually encounter this issue where inherently all points start getting very far away from each other. There are a few ways to tackle that depending on how smooth that manifold is. Another related problem is probably if you want to test whether the data is actually embedding dimension 7, you could do something more like a a global false nearest neighbors approach and just see when the false nearest neighbors end or basically plateau. That would be an approach if you just want to verify that it's 7 dimensions. I'm not sure if that answers your question. Yeah.
We'll look at it.
Yeah.
Any other questions sort of mighty small?
What was the question?
Okay, Michael, you are.
I was just going to ask questions just to.
It's the last time that you are allowed to poke him that way, yeah? I know.
So you started off the first half of the talk by saying, well, this has got stops method to do embeddings, and the way we test it is by building models to see how well the models work.
Yeah. Why did I do it for this?
Yeah.
Because this plot was made. This plot was made literally this morning at 8 a.m. in the morning.
So is it worth doing that now?
When I have time, yes.
Well, I knew the answer to that question. Sorry. This question I don't know the answer to so much. Do you think it's going to be beneficial to actually use these methods for prediction?
I suspect so. If it's able to capture and encode the actual dynamical features geometrically in a phase space, it might be better because we saw that slight performance increase when we did stops. I actually have a nice picture here of what the lobster embedding looks like based on this entropy approach. You actually get to have that loop that occurs there and the other loop, which is a big one. So I suspect possibly. Sadly, there are not a lot of multi-scale time series that are clean enough and nice enough to work with to test, but we could test it on lobster.
Yeah, because the lobster, the lags you're getting look really unique actually. You've got pairs of lags, 307, 312, and the other pair, whatever they were.
Yeah.
Clearly you've got identified some lag and you also want some derivative information.
Yeah.
That lag goes.
And in fact, it gets this small time scale twice. Once is because the difference between 312 and 307 is 5, but it also gets, 7 and 13, which is close-ish. I think the continuity statistic in the 2007 paper got 15. I don't know whether the sampling time was the same. I'm pretty sure it's the same time series. I don't know whether they rescaled it, but they managed to get 15. Yeah.
Well, you've got 7, 0, 7, 307, 314 is also 7.
There is a mistake. This actually meant to be 306 and 313, but yeah, still 7. Yeah. Yes.
Can we have a look at the reconstruction you have for the theorems? So that's toward the end.
This one?
Yeah. So in this case, your point was that it really only wanted to pick 2.
It wanted to pick 2 because probably it didn't see a very big increase in
so
picking a
think, of
third
course,
one.
The theorem system
Yeah.
It is essentially two-dimensional, right?
Yeah, and
It's just a small.
yes,
area
it's
where
this
got
small
that-
aspect here, which is that 3D
where it's
mixing.
actually important to make it three-dimensional.
Yes.
So from that, you could criticize this method by saying that it's kind of telling you the answer in average over space,
Yes.
rather than weighted to the places that are dynamically important.
Yes, so that is because here we're more looking at the manifold aspect of it. Ultimately, you have to define. Actually, you do have a maxima that occurs here. I did put a thresholding.
Sure,
yeah.
sure.
So you could argue there's a
problem
maxima
with
there.
this sort of approach in general is that you're looking at,
Yes.
you're looking at an average of the statistic
Yes.
over all space, when not all space, that's not a realistic picture of what's important to
Yeah, exactly.
unfold.
Yeah.
Are there ways that you could weight the empathy measure to try to pick out the dynamically important features?
Yes, so
like, I mean, in this case, we know where you need through that. You can actually manually reweight the data. So these points are more important, and then the question is, would it now unfold into 3?
Yeah.
And then, I guess my other question is, can you do that automatically?
Yes. So this plot actually tells you which parts of the embedding is problematic. So in this case here, if you were to do that plot up here, you'd see a very bright region in the center, followed by darkish regions on the wings, because there will be like a third layer on top of it, which is what you're actually measuring.
But in a sense, your method, if we now had noise in the system,
Yeah.
your method would be saying, okay, there's some small places here for which we get bright spots.
Yeah.
But that's kind of, we'd expect to get some places with bright spots in a noisy case.
But when you're at that case, if your noise is so big to be able to start affecting these profiles in such a significant way, you would argue that from your observation, the strength of your noise is almost on the same order as the strength of your interesting chaotic 3D stuff. So you wouldn't be able to resolve the difference.
Not over one step you can't.
No one step yet. But you could do something of averaging and doing some noise reduction with
Yeah. Dynamically.
Yeah.
But yeah, good point.
That's a basic question. So, what's the minimum number of points you prefer to analyze in a set of data?
Okay, so interesting one. So
Yes.
yeah.
I'm running at 75 for 100 at the moment, and I would guess you'd sneeze at them and say, go away.
Well, if it's 75 and 100, and if you're planning to do a low dimensional embedding, when I say low, I mean like 2, then you actually would probably be able to do it with the GCN, the neural network approach. But so one benefit of this, as opposed to the continuity one, is it is more efficient with points. And when I say more efficient, you're talking about you should be able to get results with 2,000 points. 1,000. I mean, obviously for your case, it's very, very extreme.
No, it's variable, but
Yeah.
I'm just curious for your reaction to, minimum numbers of points, and as you've already suggested, there might be a different approach according to the number, which is
Yeah.
more efficient.
Yeah, and I think the main challenge is not so much with algorithm, but more so with the inherent problems with embedding approaches in general, because every dimension you increase, the sparsity of your things start getting it becomes very bad very quickly. But if your manifold's compact, it should be okay. But how compact are manifolds, if noisy and all that kind of stuff, it's a bit yeah. Hopefully that answers the question.
I was just wanting your reaction to it, or if there was any preferred approach.
Yeah. Yeah, for low amounts of data, embedding might not be the best approach. I think that would be the answer. Embedding would probably be not the good approach for very low amounts of data. Might be better with a state space model kind of thing.
But the approach, yeah.
Yeah. Is that a valid answer?
Yeah, it is. Is there any question from the audience before I ask?
I have a question.
Yeah.
We have time to discuss this question, but I'm far away from this field for 3-4 years, unfortunately. So I don't know any advance since then. But if you use your methods and nonuniform embedding, can you avoid effects of nonlinear observability, poor observability of time series? For instance, it's known that we're on a system. You have X and Y and Z. X and if I give you X and Y, you can make a beautiful embedding. Okay? If you use Z, the embedding will be really poor, and nonlinear tools like recurrence quantification analysis, recurrent network analysis, and another one that I developed but I forgot the name, will not work with the Z component.
Yeah.
Because the Z component has a poor nonlinear observability. Okay?
Yeah.
But now I got the insight that maybe using a nonlinear, a different kind of embedding would avoid this problem from Z. What are your thoughts about it? Nonlinear embedding could prevent this.
I think if I'm thinking about the case that's very similar to that, which Lorenz tried to embed using just Z and not X and Y, which is basic. That one is like a symmetry problem, right?
Yeah, yes. The nonlinear observability comes from the symmetry problem. It's completely different from the Rosen system and other systems. Okay. So
Yeah.
it's a problem. It's a
I'm.
problem from with the time scale of Z. That's the fundamental insight.
Oh, okay.
The problem is the time scale of Z.
Yeah.
Okay. Because it runs here, then goes.
Yeah, yeah. Yeah, I mean, it could, if you could use, you might be able to use that time scale if it's due to a different time scale, like difference in time scale. But I'm not sure. You might be able to deal with the fact that it's different time scales with non-uniform embedding. How effective the embedding would be, I'm not sure on how it can tackle in general non-linear observability.
Because when you use a log transformation of Z, you recover the
Yeah.
observability and it works.
Yeah.
And there are some examples when you have, for instance, network with oscillators, and you measuring X, and from some oscillators you're measuring Z, and then you think that they are not synchronized, but indeed they are synchronized. So I was thinking maybe using a nonlinear embedding with Z, you can recover this.
Yeah.
It would be nice at least 5 years ago.
Maybe.
Now I don't know.
Yeah. Maybe.
Why is your reconstruction of Chua so bloody bad?
It's not that bad.
It's bad.
If you rotate it nicely, it's kind of nice.
Why is your presentation of the Chua system so bad?
Because I did it at 3 a.m. in the morning.
Can I ask a more philosophical question?
Yeah.
Are you comfortable with the concept of nonlinear correlation?
I mean,
Because I'm working with Ed now.
yeah.
Okay, and he gave me the red and the blue pill and said, choose or kill you. Okay, so I had an epiphany in my life about nonlinear correlation. Are you okay with the concept?
I would say here, rather than talk about nonlinear correlation, I prefer to say I'm assessing whether there's a functional dependence.
Yes, nonlinear functional dependence.
Yeah.
Correlation. Correlation by definition is linear.
Pearson correlation is linear. Ish, right?
He would kill me, so I took the
But
pill.
I think I use the word correlation more so just to get the concept across. But really, what we're testing is the
nonlinear correlation, but people, for instance, say that they try to kill us.
Yeah, yeah.
Just words. No.
Okay.
You're the last chance to grill me.
And I'm grilling you next Monday.
Wait, what?
With that, thank you, Eugene, for this nice and interesting talk. Next time, when you work a whole long weekend to get this talk, I expect more. Thank you very much. Get the music. The standard.
Because it's
But that's the point, right? You want that differentiation between the space. So I suspect you need that's why you need it. But once you have well, the rest is coming automatically. I haven't found an nice way to solve the thing there, whereas what you do Oh, okay. Hey, did I pull it off? One long weekend worth of research, did it work?
You did? You managed it. You managed to put it in a weekend's worth of work, cut it out in seconds. Whilst you talk, and you even made it into a long time. Not quite, but close.
Not a bad effort for Rush.
5 PhD students, 3 honor students, and not a lot of time.
Okay, so you've got plenty of time.
See what I come up with. I wish I could have promised so much.
No, I'm here under 8 reconstructions.
About the system, preferably text-based process.
So last week we got back because now it's Ramadan. So, and then
Where are you from?
Malaysia.
Malaysia.
I mean, but
Anyway, like I said, I'll spend the next couple of weeks.
I live in I
Analysis.
tags they were from that second goal, and ultimately obtain the same distribution on the first.
And we
goal.
But what you really want to do is
All right.
sent them a paper and asked them why. And the interesting thing, they didn't know. The interesting thing was analysis responded this morning.
I mean, it doesn't, you know a lot more about the
We'd
process.
like to get together and
You know, if you have a hypothesis process, which is, you know a lot more about,
All right.
overview.
so that much to say. Okay.
But that means
So,
that
And
the
essentially,
that's
it's
why
like-
you follow one ordinary modularity coordinates,
and nobody wanted
which covers convection,
because I don't think
because
we
you've
could
got
solve
a
this
switch in there.
equation.
So we can use that for a process to be considered.
You never know, we might get some.
Okay. Well, anyway, like I said, I'll also put some thought into what the abstract might look like.
Yes.
And that'll be in the next week or so.
Yeah,
Send something in by the end of May.
you're talking at the end.
Sorry, and what's your name?
My name's David Gildenstone.
Oh, okay.
Yeah. So I was just curious about what your problem was. Trying to apply this stuff at so different points.
Yeah, well,
It makes sense.
but it's interesting that if you, in these systems, if you try to construct the attractor using 75 points and 10,000 points, they're quite different.
Yeah, there are. So yes, when you get through enough data, you start getting all these serendipities popping up, which is very pleasant. Because as I go through the numbers, I try to stay as objective as possible, as ever it's really hard, and keep on being shocked when something keeps coming back in a positive manner. You know, you try to knock something over and it keeps popping back up again.
I'd be interested to see whatever the sort of the simplest introductory pages for people.
Beautiful. I'll send you mine from 30 years ago.
I mean, one of the interesting
You got a piece
things
of paper.
I've got a pen.
Pen.
Oh,
As
right.
opposed-
I'll write my email and just say that.
That'd be good, thank you.
One of the interesting things is that every gold deposit on Earth, I'm being very broad now, has the same attractor.
Okay.
And it's a
Well,
tool. Sorry.
That would be interesting if it tells you where to find gold.
Well,
Well, that's what some people think, yes. We went back into probability distributions for that. Then went out to 7720 that.
Yeah.
Okay.
Mathematicians, so I don't have a number.
Beauty, thank you. You don't happen to use Mathematica, do you?
I can use mathematics.
Oh, beauty. Okay.
I actually also consult for a living if you want my services. But
Okay, I went to the Wilfram Summer School back in 2019, but
yeah,
someone introduced it to me back in 1988.
yeah. I'm not a big mathematical user. I'm interested in computer algebra.
Yes, no, but I always feel such a bloody neophyte and habit of never say do it this way. You always need to fight it out, and at times
Yes.
when you can't, it's nice to have someone who will actually help. Say try this or